Hello and welcome to Explain Rust Analyzer, a video series where we try to understand Rust Analyzer one subsystem at a time. For the past couple of lectures, we've been looking into the way Rust Analyzer handles syntax tree. Our current goal is to start looking into the Rowan library, the one which Rust Analyzer actually uses to implement syntax tree. However, that library is rather complicated, so last time we started with writing from scratch a simplified version of Rowan. Now today, I actually want to continue hiking on mini Rowan. Well, the real reason for that is that, of course, hiking on a new greenfield code is always more fun than reading some existing legacy code base. But I also do think that the things I'm going to talk about today are easier to explain using this simplified example. So let's get started. Okay. Last time we looked at the green nodes, red nodes, and API, which allows us to create these lossless syntax trees. And what we ended up with is a test which constructs a syntax tree for this syntax and then even modifies the syntax tree to replace 1 with 3. So one of the things I emphasized last time is that the syntax tree is untyped. That is, rather than representing each grammar rule as a separate type in Rust, like having a type for struct or a type for a function, all of the nodes get basically the same type. So red node is a struct which holds data for structs, for functions, for fields, for names, etc., etc. And my explanation for that was that this structure allows, well, I don't think actually I've explained why we did that specifically, but there are like two reasons. First of all, it allows us to represent resilient and semi-structured syntax trees in that if you have like very strict types about like struct which has a non-null name, then you cannot represent a struct which doesn't have a name where the name hasn't been typed. If your syntax tree is sort of dynamically typed, then you can represent whatever. And the second reason for that, which we actually haven't covered, is that it provides us with a nicer APIs. So actually, let's just do this. So we had like the parent API to get the parent of the node, and we got the children API to get the children of the node. So it's easy to it's now easy to write stuff like ancestors, which just returns an iterator with red nodes. No, it's called successors. Self. I wonder if I can say self parent here. No, apparently I can't. What if we say this? Okay, yeah, this also needs to be like this, I guess. Yeah, okay, so we've got ancestors. And then it would be slightly trickier to write, but we also can have descendants. and siblings. And the way why it is at all possible to provide these general traversal APIs, which returns you simple iterators, is that we just have a single type which can represent any node in the tree. If you use strict types, then you would have to write much more windy code here to use typed visitors. So you have to define a struct, and then you have to implement a trait, which implements visit for every specific type of nodes, and there are like a lot of nodes. Such an type API is just easier to write generic code if you want to process every node. However, a problem here is that oftentimes you don't want to work with arbitrary nodes. You want to say, hey, I got a struct, which like the syntax node for a struct, and I want to get its name. And given this dynamically typed API, that actually turns out to be pretty challenging because, yeah, you cannot like get a specific node. And today we will develop the API to actually layer a proper well-typed tree on top of this raw dynamic tree. Yeah, actually, yeah, I wonder if this should be called something like din tree or something like that to give intuition about that it's untyped. In mini Rowan and Rust Analyzer, we will be calling this module AST, and that's a bit of a misnomer. It's not really abstract. The tree here would still contain all the white space, all the semicolons, all the parentheses. It's just that unlike the first tree, it will provide this API using well-typed accessors. And you will notice that I have actually typed a pretty big chunk of code here. And this code is actually really, really simple. So at the beginning of this file, you see an example, struct foo with like 2 fields. And the code below is just the code you need to create such structure using a raw syntax API. So in the AST smoke test, we have this. Why? Okay, yeah, because we cannot actually use to do with infiltrate. Yeah, you see, we invoke like a bunch of functions we defined here, and this returns this struct. Funny or maybe not so funny story. I've actually intended to just type this out while recording this video, and I started doing that, and I started joking that, hey, how cool is that the viewers can actually watch this boring copy-pasty code on 2x or just skip it while I have to type it out. And then I realized that I haven't actually changed the resolution of my screen, so my recording isn't like useful. And that's why I begrudgingly just stopped recording, typed this all out offline, and now I'm like recording and pretend that it is there. Anyway, the point here is that constructing syntax trees by hand is really cumbersome and really complicated, and you really want to use a parser for that or have some kind of generated APIs. And in Rust Analyzer, we do a bit of both. But now we have a struct, and now it's let's move the structs closer to the point where we kind of like define it. And we want to say something like struct.name. But we can't do that because, well, struct doesn't have a name field. We also want to do like struct fields. And that also isn't really possible because the type is, the whole thing is dynamically typed. But we can actually make it work. So for that, we define an AST trait. And the idea is that we will implement AST node for wrappers around draw syntax node. So we will have struct which wraps a red node, and we will have a struct field which wraps a red node. And we will have a struct name which wraps a red node. And then we will be implementing ASTs for all of those things. And actually, before I get here, let me explain one specific thing about how we want to construct our tree. So yeah, you see that the tree contains what we want to contain. However, if you, okay, we're actually missing a white space. We are missing a white space here. Always bad with shortcuts. Okay, now it's better. Now it has white space. And yeah, if you look at the structure of the tree, although it might be slightly hard to see, we actually place names of the things like this foo and bar as direct children of the nodes. So a struct node contains foo name token. That's actually not the structure we use in Rust Analyzer. If we look at the Rust Analyzer, we know that we'll notice that these identifier tokens are actually nested under name nodes. And that's deliberate because, first of all, it allows us to classify the string tokens. Like, not every identifier is a name. Another kind of identifier token is name reference. So that's kind of like the difference. This foo defines a new structure, so it's a name for a new thing. But this string here doesn't define a string. It refers to an existing string using a name, and that's like the difference between name and name ref. And having this extra layer of nodes there helps helps to write the code which need to deal with names or name refs differently. And most of the time, to deal differently means that we care only about name or only about references. And the second reason why we want to wrap this identifier into a node is that will make AST API actually easier. So let's actually refactor our code to use those. We will add make name function, which will return a node. We actually have name kind there, and children will be just a singleton array of make token identifier. Okay, and we want to change this to make name, and here we also change to this to make name. This one we actually want to change to make name ref, but we don't have name ref, and we will not be using that. Okay, let's me close the Telegram so that it doesn't distract me with unread notification. Okay, let's rerun the smoke test to check that it compiles. Yeah, so you see we get exactly the same text, but now the structure of the syntax node is different. We actually do have extra name in there. I wonder if can do this to type it out. Yes, so somewhere here we will see a syntax kind for name, which would be syntax kind 2. So yeah, here is this name, which contains a single token. Anyway, so basically, yeah. The idea is that we want to layer types using like the standard pattern where you start with an untyped thing and then you wrap it into a new type, and new type just enforce an invariant. Then an untyped thing inside actually has a specific shape. To do that, we need only one method. Which takes a red node and returns an option of self. And then it will work in a rather simple way. So if node kind is struct, then we return the AST node, and else we return none. And we repeat this for all the AST nodes we have. And again, you see that even for 3 nodes, that is a lot of boilerplate. And the real Rust language has like 200 different AST nodes. So there is a lot of boilerplate. And we just generate all that in Rust Analyzer. So yeah, code generation is a good thing. And now that we actually have this, we can start writing a lot of utility functions. So for example, we can write a function which returns a struct name. And what it does is it takes the red nodes, takes its children, I guess I could even write this like this. Takes the children, which are nodes, and then finds the node of a specific type. Let's see, okay, let's add a where clause here. Okay, the last one should actually be find map. And we cannot compare syntax kinds, which is kind of really stupid. No, I should have done this. Because like the primary thing you want to do with syntax kinds is actually to compare them and to match them in much expressions. Okay, this should be field and this should be name. Okay, so now we print a struct and we can actually print a struct's name. No. Let's say, because that struct is like still untyped struct, but now we can say let's actually cast this to a well-typed one. Okay, yeah, and structs are implemented for red nodes. So we also need to write this, wrap this into new root, and new root returns red node. So okay, now it should work. Yeah, I wonder if I can say I want to implement display here just to make this more convenient for us. I wonder if this will pass. No, that doesn't parse coherence check. So in Rust we just generate display impl for any struct. Here we will be using like .0 to see what things are there. So yeah, we can now look at the struct, but we also can ask for a struct name and print a name. And unsurprisingly, this doesn't seem to work. Why is that? Okay, yeah, because yeah, while I copy pasted everything, I actually didn't update the thing. Yeah, okay. So now we can print struct and we can access its name. Similarly, we can add a name API to a field because fields also have name, and we also can actually automate this a bit and say that we actually can get any child with specific type by basically copy pasting this. Oh, right. Because cast is only one side of a question. Another thing we need here is we need access to row syntax node. So casting an untyped node to typed node, like wrapping a typed node around a typed node means that you have a cast function which can fail and which goes from untyped to typed direction. But you also have a syntax function which goes in the opposite direction. If you have a typed function, then syntax will return a red node. And syntax will look identical for all of these. It will just return a first field. Okay, so I'm not feeling well here because I've typed out a lot of code and I'm not sure if this actually compiles anymore. No, it doesn't compile. Child of type. Okay, obviously it should have self. Okay, it works. So this can now be just child of type, and the type will be inferred from the return type, and similarly here. What's more, we can actually now have not only a single thing, but we also can have an accessors to iterate many children with specific types. So for example, struct contains many fields, so we can have something like this. And that's basically it, except for the final find map. By the way, fun story. I think it was me who proposed or even maybe added the find map method to Rust.NET library, and that was specifically to make writing Rustlizer code easy, because this pattern where you filter map and find map some AST node : cast is everywhere, and it's really convenient that you can do it. Anyway, actually, like, ideally we would like to have children of type method on a trait itself, which returns an iterator, but that well, that can't return an impl iterator, and you can actually write this all by hand, but it's got tedious, so let's just hard code it for a struct. Okay, check if this is compiling. No, it doesn't compile because we still need to declare our lifetimes. And okay, filter map, field cast. Okay, perfect. So now we can write things like struct fields and let's like enumerate it. Yeah. So this works. Note that I attach white space to the fields. That's why there's extra white space here. And that is how you actually create a nicely looking and convenient to use API on top of type syntax tree. Let's also print a name to show that we can access both collections and individual children. Yeah, so that looks reasonable. An interesting thing here, well, a couple of interesting things. First thing is that you'll note that the name method on a struct returns an option. And that is because we want to, although struct names are required by the Rust grammar, we actually want to be able to represent invalid syntax as well. So basically everything which we have as an accessor will return an option. The second interesting thing is that this flexible and dynamically typed underlying syntax tree actually yields itself very naturally to providing robust typed APIs. So, for example, if we break the syntax for our struct and like just don't emit a name, then obviously that unwrap inside a name will panic. But if we comment it out, we still will be able to iterate fields. So this style of APIs allows you to get typed access even to completely invalid code, and that's why it's like a very good fit for writing IDEs. One thing you might notice and might have cringed at is that in a typical AST, accessing, say, a name of a particular node, it's constant operation. We just do a field offset because the name is just a field. Here we actually have to iterate all the children, and that feels pretty bad. And sometimes it is indeed bad if you have a lot of children and you are asking for the child which isn't there or is the last one. But it turns out that this actually works pretty nice for an IDE because most of the kind of like you have nodes of two types. Nodes of the first type have only few children. Like they have, I don't know, like say 5 children of a specific type. And for this, yes, it's kind of like extra overhead to get a last node because you need to walk through the first 4 and compare their kinds, but it's not so bad. The second kind of nodes are nodes which can have arbitrary number of children. For example, a field list and a struct can have arbitrary amount of fields. And that by itself isn't actually bad because you do not write a code to access the last field. You always process fields and bunch. You want to iterate through all of them anyway. The failure mode here, which you need to be aware of, is one when you combine those two. When you have a bit of a when you have some number of strictly type children, and then you have an arbitrary amount of children of a specific type. Yeah, I guess it's like very confusing, but it's simply just to look at the difference between how this struct is represented in our tree and how it is represented in Rust Analyzer. So in our tree, you'll notice that we make fields direct children of a struct node. And that's actually bad, because if your struct, if you say write the code to access a closing curly brace, and your struct has 1,000,000 fields, then that becomes slow because you need to, yeah, that's kind of a bad example. Yeah, a better example would be like this. Say your struct has like 1,000,000 fields, but it doesn't have a name, and parser like correctly recovered from it. Now, a lot of code in an IDE would actually try to look at this struct name. And every time when they look at the name, they won't find this name. But to figure out that there isn't a name, the code would have to iterate all the fields many times. And that's slow. And the idea here is to make this pattern impossible on the syntax tree structure layer by just not putting the fields directly under the struct. So if we look at the syntax tree for an actual Rust Analyzer parser, then we'll see that this arbitrarily long node with many children actually has a dedicated node for it. So we have a record field list, and it's the record field list which contains all of the fields. So if this struct misses a name, then we would still have only a constant number of children to check for, because the arbitrary number of fields is nested one level deeper. Okay, I guess that's all I want to cover around AST nodes this time. There's a bunch of fun things about code generation, but we will be covering that separately. Okay, let me think for a moment what we'll be discussing next. Yeah, I guess that's all for an AST. Let's now go to a different topic, the topic of pointers. And before we will look into that, I want to quickly call out one peculiarity which you might have noticed. So, when we speak about green nodes, we wrap them into atomic reference counts. But when we speak about red nodes, we actually wrap them into non-atomic or non-thread safe reference counts. Why is that? Well, uh, the idea here is that we want to allow using a syntax tree from many threads. We want the syntax tree to be thread safe, but at the same time, we want to exploit the fact that most of the processing actually happens on a single thread. And that's why, because we have like these two trees, you can actually share a green tree between separate threads. But if you want to traverse through the tree in separate threads, each thread will have to create its own copy of a red tree, which red trees will just share the same green tree. And then each thread can use red trees, which are cheaper because they are using reference count. In this implementation, that's kind of like not really interesting because each red node contains a green node. So you still have to increment the reference count for that green node, and incremental atomic reference count can be pretty slow because it requires synchronization between different CPUs. But we will see how we will exploit this in the real Rowan. Anyway, let's say we have two threads which process the same green node using two different red nodes. And let's say that thread A found an interesting red node, and it wants to tell about this red node to another thread, to thread B. The problem here is that it cannot just send this red node through some kind of a channel, because, well, red nodes are not thread safe. And that is the moment where we introduced syntax pointers. So syntax pointers is a way to describe a position of a tree, a specific syntax node, without actually storing the actual node. So if we have struct char, then we will have I guess it's can be called address. So this will take red node and return its address somehow. And another operation is to dereference a pointer. We will take a pointer, a root of the syntax tree, and what we will get back is a red node. So the way and pointer will be send and sync. And so the way this will work is that in threaded in thread 1, we will find some red node somewhere. And then we'll create a pointer from it. So, okay, and should I say that we started with some green node? And thread 1 gives a copy of green node. So red node new. And then thread 2 gets a red node. Let's say they also have like some kind of a channel to pass the data between them. So yeah, root children find map something something. Does it matter as long as we get a red node back? And then we get an address, and then we use a channel to send this address. The second thread will receive this pointer, and we'll pass the root node to it. And the end result would be that these two red nodes would actually be two different objects in memory with two different reference count, but they will semantically represent the same underlying syntax node in a tree. Okay, the question is how we can implement this pointer. Well, there are two possible representations. First is we can represent it as a sequence of steps. Where the sequence of steps means like the sequence, let's say 1, 0, 2, 0 means start with the root, then go to the first child of the root, then go to the 0th child of that child, then go to the second child of that child, and finally go to the 0th child of that child. So basically we have a current node, initially its root, and then we iterate through steps and assign the current node to the specific child of the current node. A different way to represent this is to say that a node is identified by its range in the text. So for where is our example? I've deleted the example, too bad. Okay, yeah. For something like this, so if this tells us that, okay, it doesn't tell us how many characters are selected there. So if this tells us that 17 characters are selected and this tells that 28 characters are selected, then the range of this field is from 10th to the 28th character, and we can use this range as a pointer to the node. And I think it's pretty clear how you can write these address of and dereference operations for both of these representations. In the first, you just go to the nth child. In the second, you should just find a child which contains the specific range. One non-obvious issue here, though, is that with the current API we have for red nodes, let's look at it. The current API only allows us to access children one by one. We start with the first child and then we iterate to the next child. And that is because each child, each red node, needs to preserve its offset in the text. And to preserve offset, well, you need to compute this offset in parent thing. And to compute offset in parent, you actually need to iterate all the children before. And that means that both of these representations would actually have linear worst case complexity, meaning that if you have a child with million nodes and you take a pointer to the millionth node, then, well, dereferencing this pointer will have to traverse all the million children. And that is pretty bad, because then if you create a pointer for every one of those million children, and then dereference those million pointers, then you will have to do million squared operation. And the kind of like, I guess million children isn't reasonable for real syntax trees, but there is definitely syntax trees with thousands of children. And even thousands squared is still pretty big, and it can result in like reasonable lag in your IDE, not to say about unreasonable CPU consumption. So we need to do better. And the way to do better here is to modify the green structure. So in the green tree, rather than storing a list of children, we can actually store a list of pairs, where the first pair is an offsetting parent. And now, when you have this additional information stored in the green node, you gain the new operation. You gain and child. Which returns an option, and I wouldn't be actually implementing this, but this will be working in O1 time rather than ON, like we can do with the current implementation. What's more, we won't be able only to, not only will be able to get the nth positional child effectively, we will also gain the operation child with range, which takes let's call it child containing range. And the semantics of this operation is that we take a text range and find a child which contains this range. And that can be done using binary search in logarithmic time, which is much more efficient than the way we can implement this operation currently. Again, currently we can only do this linearly. And having those two functions, you can use these to implement pointers using sequence of steps, and you can use this function to implement pointers using text range. And yeah, in Rust Analyzer, we actually originally, like not really originally, but for until the very recent times, we used this representation, which didn't have these partial sums for offsetting parents, and we did have these accidentally quadratic behaviors when dereferencing certain pointers. But recently we switched to this implementation which stores more data in green nodes, but is significantly more effective for dereferencing pointers. So yeah, I won't be implementing this right now, but this is something which we will be keeping an eye on when reading the actual Rowan implementation. I guess one last thing I want to tell you when discussing pointers is that this example with separate threads is actually not something which we use. Like it's, I don't know when you actually want to transfer syntax nodes from one thread to another. In real code in Rust Analyzer, there is a very different, well, kind of similar but different use case for pointers. And this is rather than communicating syntax node in space from one thread to another thread, we use syntax pointers to communicate nodes in time. So we create a pointer to a node at one point, and then sometime later, we use that pointer to retrieve the node again. And the motivation here is that you can parse a file into a green node, process it, store a bunch of pointers to interesting nodes, and then you can forget about the original file. And forgetting about the original file is pretty important because syntax nodes are a relatively heavyweight data structure. So it's important that you are able to process them and evict from memory. But you can still persist pointers. And pointers take much less space than the actual syntax node because they don't have to keep the whole tree in memory. And then if at some later point you realize that you actually do need access to the actual node, well, you can recreate the syntax tree from scratch by reparsing the original source code, and then just use the pointer to dereference it and to get to the right node you're interested in. Okay, I guess that's it. And now I am even more certain that this was the last lecture where we looked at the mini Rowan implementation. And next time we will finally start looking into actual Rowan. Thanks for watching.